Okay, we're going to talk a little bit about symmetry of graphs now. So I'm going to first just talk about what this means, to be symmetric with respect to the x-axis, not just in terms of what we're looking at, but in terms of the algebra. So if it's symmetric with respect to the x-axis, it means the picture is a reflection, through this axis, and so if you folded it in half through the x-axis, one half would lie on top of the other half. So it could be, maybe a parabola, something like this, and be better if I had a picture that I had pre-made, because my drawing's probably not the best. But basically what you have here, it can't be a function because you would have, 2 points lining up vertically. But if you have the same x here, and say this is y, then the opposite of y has to be on the other side. So anytime xy is on the graph, then x negative y is also on the graph. Well, we could write that all in words, but I'm not going to write it down. You can write that down if you need to. So every time xy is on the graph, x negative y is also on the graph. So if we were going to test for this kind of symmetry, we would actually replace negative y with, or y with negative y, and see if we have that symmetry, which we're going to talk more about that idea with even odd functions. Now this one wouldn't be a function, of course, but we'll come back to that idea. We're not going to test for this type of symmetry. We're not going to spend a lot of time on this. I just want you to be familiar with the ideas, okay? Alright, symmetry with respect to the y-axis. Then, of course, in this case, we can have a function because it would, let's say we have the V-shaped graph here. It would, we could have something like this. Now, you can have a graph with both symmetry with respect to the x and y-axis, and then of course you wouldn't have a function. But if it doesn't, have the symmetry with respect to x and just to y, then you will have a. Well, I'm trying to think here. I don't want to say that as an absolute. Yeah, you will have a function here. Well, I guess you can't really say that because you could have, something like this, but this one is a function. Okay, let's just say that. So in this case, if you have xy on the graph, then over here you've got this mirror image through the y-axis. So this is the same y coordinates, but the x's are the opposites, negative xy. Okay, and then symmetry with respect to the origin means that's basically rotational symmetry. If you rotate through the origin 180 degrees, your graph will look the same. Algebraically speaking, that means that a common example would be this one. If xy is on the graph, then when you rotate that, it comes down here, and these are both opposites then. If this is x, this is negative x. And then if you go up y here, this is down y, so that's negative y. So with symmetry with respect to the origin, anytime xy is on the graph, then negative x, negative y is on the graph. Okay. So as long as you have a graph that passes the vertical line test and you have symmetry with respect to the origin, that is, of course, a function then, and it's actually called an odd function. And anytime you have a function that has symmetry with respect to the y-axis, like this one, those are called even functions. And so in terms of function notation, I'm going to redraw this in terms of function notation. Of course, this one's not a this can't be a function, but we just mention it here for completion. But these two types of symmetry can yield a function. Now, some graphs will have all, like if you had a circle, right, like around the origin, it has all three types of symmetry, but it's not a function, so we're not talking about that in this case. Here's just even odd functions. So an even function has symmetry with respect to the y-axis. So if this is y equals f at x here, then when you plug in x, or you plug in the negative x, the output is the same. You get f at x for both of them, right? So you plug in x, you get f at x, and you plug in negative x, but it also is equal to f at x. And that's what the definition is saying. If these two things are equal for every possible x in the domain, then you have what we call an even function, and that has symmetry with respect to the y-axis. When you have an odd function, so now I'm going to look at this one and say we call this y equals f at x again. So here you plugged in x and you got out, we called it y originally, but that's f at x. And then here you plugged in negative x, right? These are the opposite signs. And you got out the opposite of y, or the opposite of f at x, which is negative f at x. But what you actually plugged in was the negative x. So this is the relationship we're looking for right here. That when you plug in negative x, the opposite of x, your y also ends up being an opposite of the original point. Okay? So you plug in the opposite input, you get the opposite output for y. These are how we test. So this is our test. So let's do a couple of examples. The first one, want to know if the function is even, odd, or neither. Of course, not every graph has symmetry at all, so lots of graphs will have neither one. But for even, odd, then we need to satisfy one of these two. And so what I always do is I start with the f at negative x, because that's the same in both of these definitions. And then you simplify it. If you end up with the original function, then you know you have an even function. If you end up with the opposite of the original function, then you know you have odd. And if you don't get either one of those things, then you know it's neither. Okay, so back to this. Let me grab a drink here. Excuse me. Okay, so f at negative x, start with that. It means we're going to plug negative x in for the x's. So we got negative x to the fourth minus negative x squared minus 3. And because of the even power, this negative x to the fourth, if you will, you could think of that as negative 1 times x to the fourth. Whoops, like that, excuse me. And so you've got negative 1 to the fourth times x to the fourth. Negative 1 to the fourth is just 1, so that reduces to x to the fourth. Anytime that's an even power, the negative, you have an even number of negatives and it becomes a positive. So you get x to the fourth minus x squared and then minus 3. And notice that's what we started with. That is f at x. So f is even. Okay. And the power, the even power thing is, kind of what that's where the name comes from, but you have to be careful because not all functions deal with powers. So you don't want to just generalize and say, oh, I just look for even powers, because that's not always true. I'm going to graph this on my graphing calculator just to show you the symmetry. Okay? If you don't have a graphing calculator, I don't let you use one on tests, but you don't have to go out and buy one, is what I'm trying to say. There's lots of graphing apps, for your iPads, if you have an Android tablet, whatever, you can get an app, or even on your laptop, just go on the internet and Google graphing, and you should be able to come up with some free graphing site that you can graph with, and you don't need to go out and spend money on a graphing calculator. Okay, so anyway, back to this. X to the fourth minus x squared minus 3, and then let's see what my window looks like. Okay, that's how I like it. So then graph. So you can see the symmetry through the y-axis there, right? You can zoom in a little if you want. Well, that kind of cut off the bottom, but you can see. Let me change the window. I wanted to see the bottom. Let's try 6. There we go. You can see there's a little dimple there, but we have symmetry. Okay, let's move on to G at x, we have this function here. So again, start with negative x, plug it in for x. Now because of the odd powers, so I'll just do the negative x cubed, but this is generalized to any odd power. We've got, that's negative 1 times x, so negative 1 cubed times x cubed. Negative 1 an odd number of times will give us negative 1. So that reduces to negative x cubed. And of course this one, there is no power, it's just minus x. 2 times negative x cubed is negative 2x cubed. Alright, so if we compare this to the original, opposite sign, same sign. So this is not, obviously this doesn't equal g, right? So it's not even. I should say, so it's not even. But it also does not equal negative g at x. And if you don't believe me, well, consider negative g at x. That would mean you put a negative in front of the function given. Every sign needs to flip then, and that's not what happens in this expression. Notice these two are fine, but then this is not the same sign, and so that's not equal to negative g at x, so it's not odd either. And this one then is neither even nor odd. Let's see where I'll write it over here. Okay, so I'll graph that one. The graph should always back up with your algebra. I want you, I just want you mainly to be familiar with these concepts because they will, especially in trigonometry, if you take trig, you're going to need to know the difference between even and odd because the trig functions are, all of them are either even or odd. So the algebra here, you should be able to do this algebra. Alright, what am I? Oh, I was going to graph this, I'm sorry. So y equals 2, let's just clear it out, 2x cubed plus x plus 1 graph. Okay, so it almost, let's change the window. There we go. It's kind of similar to that first one I showed you that was odd, but it's actually off. It doesn't go through the origin, and so you don't have that rotational symmetry. So this one is neither even nor odd. Okay, we're going to leave that idea behind then and go on to the next topic, which is the zeros of functions. So zeros is a word in mathematics that basically means when you're dealing with a function, not the number 0 we're talking about here, but for a function, when we talk about zeros, we're talking about the numbers that make the function equal 0. So what inputs give us an output of 0? If we're going to graph the function, that means those, because this is y equals 0, right? That's where the output is 0. That's going to be your x-intercepts then. So when we want to find the zeros of this function, we're going to do it algebraically, but we could also look at the graph. So y equals 2x squared minus 3x minus 5. So you can see it looks like there should be two answers. We've got two x-intercepts here. And one looks like -1 and the other looks like about 2.5. And we're going to see if those are the answers. So when we want to find the zeros, we're going to solve. We want to know when is f at x equals 0. Well, that means when is 2x squared minus 3x minus 5 equals 0. That's a quadratic equation, which you should know how to solve. Wow, I'm losing track of my letters here. That's a QA, a QUA. I'll just start over. Okay. So if you can go straight to the quadratic formula if you like, or you can try to see if it factors. This one will factor. The 2x squared is 2x and x, and then negative 10. We'll get negative 5 plus 1. There we go. So we get negative 5x plus 2x adds up to negative 3x. And then set each factor to 0. And this gives us x equals 5/2 or x equals negative 1. Those are the zeros. And that, we saw that, you know, on the graph as well. So we know our answer is correct. All right, so you don't need the graph to answer the question, but it's nice to have the graph to kind of back up and see that if your algebra is making sense. Okay, in example 7, this one looks more complicated, but the idea is the same. We want to know what numbers can we plug in this thing that will give us 0. So we want to solve h at x equals 0, or in other words, this whole thing equals 0. Well, the problem looks harder than it is actually, because the denominator, it doesn't matter what that is down there, that's not going to yield a 0 for us. It's only going to be 0 if the numerator is 0. And you can get rid of this denominator by multiplying both sides by 2x minus 5. And notice that will cancel then on this side, and 0 times anything is still 0. So really, we're only going to get a solution if the numerator is 0. Okay, this denominator doesn't affect the solution. All right, well, later we're going to learn how to solve this if it doesn't factor. But this one factors, and hopefully you remember how to factor. If you don't, you should go back and review factoring, but specifically by grouping. When you have 4 terms and they don't have a common factor, you know, like these 3 all are divisible by 2, but this one's not. These 3 all have an x, but this one doesn't. So all together, all 4 of them don't have something in common. You need all 4 to have something in common. So it's not a greatest common factor problem, but it is, if we do the grouping, group these 2 and group these 2, then we can proceed. The first 2 have a common factor of x squared, and then we have x minus 2 left behind. The second 2 have a common factor of 4, but in order for this to work, we want what's left behind here to be x minus 2. So if you only take out a 4, the signs are going to be wrong. So you actually want to take out negative 4. And then these are the same, and that's what we want. So notice if you redistribute, you get back to where you started, and that's your check to make sure that you factored correctly. Now we're not done factoring because we still have actually 2 terms separated by this subtraction. The reason we want these to be the same is we're saying, okay, here's my 2 terms. What's the common to both of those things? And if these binomials aren't the same, then there's nothing in common. So the x minus 2 is what's common. You take it out of there, and you're left behind with x squared minus 4. And then x squared minus 4 is the difference of 2 squares, so that actually factors some more. It's x plus 2 times x minus 2. All right, so this is this one, and then these 2 come from this. So we actually have 3 binomial factors. Set each one to 0, and we get x is 2 from this factor. Set this one to 0, and we'll get negative 2. And then this one will give us x is 2 again. So we don't need to list it twice. There's just 2 zeros, x equals 2 and negative 2. Okay, so that's some terminology. You know, we're just kind of setting the stage for maybe some new ideas. New terminology for things that we've kind of, you know, we've solved things like this maybe in the past, probably not with the denominator, but you should have at least solved something like this. But you probably didn't call it a 0, right? It's just a new word. Okay. Well, let's review slope. So slope is of course, something we talk about when we're dealing with lines, right? Lines have a slope, and the formula for slope, I didn't write it down here, but just to review, we've got our change in the y coordinates over the change in the x coordinates. And of course, we can't have the denominator equal 0, so we say x2 can't equal x1. So you should know this formula already, and you should know how to find the slope of a line and find an equation of a line. If you don't know those things, go back and review. They're in chapter 1 and section 2.1, which we skipped, right? What I want to talk about here is the slope as a rate of change. Because this is a change in y over change in x, this is a rate. You've got the change in the y, how many, I'm sorry, I'm losing my train of thought here. If you think of your graph, how much does y change per unit of x? That's what I wanted to say. I think I have that typed up here, yes, right here. So there's per here. We've got y units per x units. So if we're doing an application and we have, not just generic units, maybe y, the change in y is in dollars and the change in x is in months, so dollars per month or dollars per year, or we're talking about miles per hour, things like that. These are all rates is what I'm getting at. So in this example, I've got some linear functions here. And remember, back to, I think I actually have this typed up in the next section, but that's okay. Just think about back to y equals mx plus b, right? That's a line with a slope of m and an intercept of b. Those are linear equations. I didn't type that up here, so this, I'm trying to remember what I typed in here. Okay, has slope m and intercept b, right? So that should be a review. So if we replace the y with f at x, then it's a function. We can see from what we talked about before, y is isolated, so we do have a function here. So this linear function, f at x is 2x plus 10, models the amount, f at x, in billions of dollars that the drug industry spent on marketing information about drugs to doctors x years after 2000. So in this problem, we want to interpret the slope as a rate of change. And so the slope is 2. And then I say use the correct units. So the slope is 2 means something is changing 2 units per 1 unit. And here's where understanding the labels is going to help you. The x is measured in years, and the y is measured in billions of dollars. And so this would be, billions of dollars per, and then this should be, you want to think of your change in x as a 1 unit, so per 1 unit. This would be years, 1 year. And because it's a plus, it's an increase of $2 billion per year. So the interpretation is that the amount the drug industry spent on marketing increased $2 billion per year. Let me write that down. I already got the dollar sign here, so I'm not going to write down dollars. $2 billion per year, and I should say after after the year 2000, right? Okay, let's do another one. So here we have this function. It's again a line, mx plus b form. F at x is negative 0.28x plus 1.7. Okay, so first thing is, identify that slope, negative 0.28. So this is the model's the percentage f at x. So that means y. The y coordinates are percents. Percentage of taxpayers who were audited by the IRS X years after 1996. Sorry. So again, X years. And so the change in y, slope is change in y over change in x. So that would be negative 0.28 it's a percentage for the y. And then for the x, per unit x, so per, whoops, I already did the per right there. Don't need to write per year. Okay, so we want to interpret this though, not just label it. So the percentage, and notice the negative here, that means it's a decrease. So the percentage of U.S. taxpayers audited, sorry, I'm working against the clock a little bit here. I got to leave in a minute, so that's why I'm rushing. I'm sorry. Audited after 1996 decreased, that's the negative part, by 0.28%, I'll just use a percent symbol, per year. Okay, so I don't put the negative there because that's the decreased part. I've already taken care of it with the decreased. Okay, all right, like I said, I do need to get going, so I'm going to stop the video and then I'll finish this last concept, which is average rate of change, in the last, third part of the video. So I put this in this section. It's not really, in the textbook. I put it in here just because it will help us with this idea of the average rate of change. So with a line, we have a constant rate of change. This change, when you think about your line and your slope, if you know the slope is 2, say you're starting at, let's say we start at 0, 0, we know we go up 2, right 1, up 2, right 1, up 2, right 1, right? And it's always on the line, and the rate of change is constant. So in this next concept, which we'll talk about in the next video, the rate of change for the function is not constant, but we can talk about the average rate of change. Okay, so that will come in the next video.